Hello, everyone. Thank you all for joining me today. It's Friday evening for those of us in the EU time zone. And oh, look at you. It's already midday for those in the mid coast. And thank God it's a Friday morning for my California homies in the US, including New York. Wherever you are joining us from, it's great to see you here, and we appreciate your interest and time, your precious time out of your busy schedule to be here to learn about Celo. Study shows kids don't learn very well if you are hungry or thirsty, so feel free to grab your bowl of cereal for your breakfast or popcorn, drink or coffee or water, whatever suits you. We ain't judging, so get your learning groups on. And for those who are attending this session for the first time, I'm Judy Piper. I'm rather famous now. I'm one of the engineering leads at Celo based out in Berlin, Germany. And I'm also the host for this Celo Tech Talk series. Celo is a mobile-first full-stack blockchain platform with a mission to build a financial system that creates the conditions of prosperity for everyone. We recognize this is an ambitious mission, and we're building Celo with our end users and also the Celo community. For this reason, we started the Celo Tech Talk series to share and spread the Celo technology knowledge with the growing Celo community. We have a Q&A session at the end of this talk, but you can use the Ask a Question menu to add your questions at any time. And friendly reminder though, that this is a Celo Tech Talk, so keep your questions relevant to the Tech Talk topics today. And we wrapped up the sessions on building on Celo last week. And this week, we're switching our gear to focus more on the Celo's contracts and primitives tech components. Today's presenter, York Rose, is no stranger to Celo Tech Talk. He and Amy Swanson gave a Celo Tech Talk on governance last year, and he's back with us today to talk about Celo's contract release process. Welcome back, York.
Thank you, Judy.
Before we get started, I'm going to have to ask you to introduce yourself and what you've been working on.
Cool. Hi, guys, everyone. My name is York Rhodes. Thanks for the introduction, Judy. I work on the contracts and primitives team at Celo, and in the past, I've worked on a few other smart contract projects, some voting standards, and token curated registries, if you're familiar with that project. And I'm super excited about the power of smart contracts. And today we're going to be talking about that on Celo. So thank you guys for joining. And if there's any questions at any time, just throw them in the chat and we'll get to them either in the moment or at the end. So without further ado.
Let's do this. So I'm going to go background now. It's all yours, York.
Awesome. Okay, so as Judy mentioned, at Celo, we have a super ambitious mission, which is to build a financial system that creates the conditions for prosperity for everyone. And as a consequence of this mission being really ambitious, we have a full stack approach to achieving this mission. And in this approach, there's three fundamental layers to the technology stack. And my team, the contracts and primitives team, focuses on innovating in the middle layer. And if you're not familiar with smart contracts, generalized smart contracts were first fully realized on the Ethereum network. And it's a technology which enables code that can define complex digital and financial relationships transparently and trustlessly. And on Celo, this tight integration between the blockchain layer and the applications layer, or rather design motivated by the application layer, comes with a unique set of capabilities and accompanying design challenges. And we're going to be kind of addressing some of those today. So on Celo, the unique challenge for smart contract developers is building systems for end user facing applications. And this requires an ability to respond with agility to user feedback while maintaining the trustless relationship our users have with the technology that makes smart contracts such a powerful innovation and technology. So the smart contract release process on Celo is designed with this North Star in mind. So today we're going to hopefully eventually understand all of the components of the smart contract release process. But first, I'm going to introduce what the Celo core contracts are, do an overview of our decentralized governance process, talk a little bit generally about smart contract upgradeability, and then talk about our development workflow internally and a release process that all of you guys can actually participate in. So look out for that coming up. And then we'll have time at the end for Q&A, and you can also at any time drop questions into the Crowdcast box. Cool. So what are the Celo core contracts? So on the Celo network, unlike the Ethereum network, there is a set of core contracts which provide fundamental functions for the entire stack to take advantage of. So both the applications layer and the blockchain layer are using these core contracts. And again, this is kind of a benefit of the way our stack is set up. And the registry contract is used to keep track of the core contracts and allow them to interoperate with each other, as well as allow other contracts to interoperate with the core contracts. And it's very easy for contracts to communicate with each other using this registry, which is essentially just a hash map that is at a specific address. And without these feature components that you can see on the screen here, which are defined by the core contracts, most of the value propositions for our users aren't possible. So users of applications like Valora, if you're familiar with Valora, our mobile app, users of Valora couldn't send the Celo dollar to any cell phone number around the world without many of the contracts you see here. So we need the identity feature component here to create a mapping between users' cell phone number and their corresponding on-chain key pair. And we need the stability mechanism, for instance, for the Celo dollar to maintain a stable value and have a strong utility for our users. And then on the other end of the spectrum, the operators of nodes on the network, so validators or full node operators wouldn't have an incentive to participate and maintain their infrastructure without our proof of stake protocol. And basically our coveted 5-second settlement times, which give us kind of some unique advantages over Ethereum, wouldn't be possible without these contracts. And even software developers like maybe you or I would not have built-in incentives to continue growing the value of the Celo network through additional applications and additional blockchain improvements without these contracts. So kind of all of the value that is provided by the Celo network in some way or another touches the Celo core contracts. And so there's this ecosystem of stakeholders on the network. The end users who use the mobile applications, the validators, the node operators, the developers, all of these stakeholders can participate in quite complex financial relationships between each other without trusting each other or even having knowledge of each other's identity due to the security properties of smart contracts, namely immutability and transparency. So even C Labs, the kind of original developers and contributors on the core contracts, have no special ability to manipulate what the contracts do or how they function. And so what is decentralized governance? Decentralized governance is a way for this diverse ecosystem of stakeholders to decide how the core contracts should evolve and adapt to kind of user needs. So I borrowed this from my previous tech talk, but the governance process allows the Celo community to make decisions to change the platform. And in the simplest terms, it's a voting system. And you participate by voting with the Celo token, which can be earned or acquired through various means, whether it's a community grant or various reward programs we have for voting and validating, a rewards program we just rolled out to the Valora mobile application, developer bounties. There's a lot of different ways to earn the Celo token, and you can basically participate in the evolution of the platform by staking this asset, or rather locking this asset for a predetermined amount of time. And we have this Celo improvement proposal process, which is a lot of which is borrowed from the Ethereum improvement proposal process, or EIP process. And this functions as a forum for developers to discuss the future of the platform. And my team, the contracts and primitives team, facilitates the discussion here. And often this manifests as design advice or implementation support, but this is where the potential changes that developers are working on are discussed and worked on. And in order for these changes to actually be enacted in the core contracts, we have a governance contract in the Celo core contracts that all of the registered contracts have explicit knowledge of through the registry. And these contracts restrict elevated privilege functions to be callable only by this contract's address, giving the governance contract the exclusive ability to make administrative level changes like modifying parameters which might significantly impact the function of the core contracts. And this is the way that we can allow the community to make changes to the contracts. Basically, we can discuss the change on the CIP forum, and then at any time, the contents of one of these CGPs, which is a Celo governance proposal, can be proposed on chain and submitted to the governance contract by any Celo holders through the contract's propose endpoint or function. And within the governance contract, these proposals are simply a sequence of encoded transactions to be sent from the governance contract to other contracts. And so that might be saying, changing a parameter of the stability mechanism or of the blockchain parameters. We saw here that in this example, we are changing an exchange parameter called the reserve fraction. And so this is just a transaction being sent from governance to the exchange contract, which calls like set reserve fraction. And once a proposal is submitted to the governance contract, it manages the life cycle of the proposal within the contract itself. So the Celo community and all of the different stakeholders can read about the proposals by using some of our tools to query the governance contract. And they can vote using their staked Celo or their locked Celo to indicate their support. And if these votes reach the constitutionally defined quorum for both agreement and participation in the referendum phase, the proposal can be executed, which again means actually executing these transactions, which are stored inside the governance contract. And so in the context of smart contract upgradability, there is some complexity in this because we want to be able to, through decentralized governance, make upgrades to the logical implementations of contracts. And in general, smart contract upgradability is not a novel concept at all. You can see on Google, there's 170,000 results. So clearly, like, a lot of people have been thinking about this for the past few years. And the reason for that is that there are all of these different Ethereum smart contract systems that have accrued immense value. I think like the total value locked across Ethereum's DeFi community is something like in the tens of billions, if not hundreds of billions. And these systems inherently, because of how widely used they are and how much value they have, they eventually necessitate either a bug fix or a feature improvement or some way to patch a mutable smart contract. And again, immutability is one of the security properties of smart contracts that make them so powerful. And so upgradeability, or the decision to basically break immutability or make a contract mutable, shouldn't be taken lightly because it modifies the security properties of smart contracts. And so there's this company in the space called Open Zeppelin. You can see it's like the first result on Google, who's come up with this design pattern called the proxy storage pattern, or proxy unstructured storage pattern. And this has been adopted super widely across a lot of different smart contract systems on Ethereum. And the basic idea is to separate the storage contract from the implementation contracts, such that we can have a persistent and immutable storage state while allowing for an upgradable or mutable logical implementation. And this comes with the caveat that new implementations must maintain storage layout compatibility with old implementations, because there's a bunch of logic which depends on where that storage is defined. And so what this means is that this problem of backwards incompatibility creates a lot of inherent risk in the proxy design pattern and upgrade process. Because developers who are working on contracts might be working kind of in an asynchronous environment on a bunch of different unrelated features in a Git repo, and changes might seem backwards compatible, but when merged or something, they become, in fact, incompatible. And even more scarily, the implementation changes as discussed in a forum like the CIP process might not even correspond to the implementation, which will actually be enacted in a governance transaction. And so because of the amount of risk here, there's some well-respected security firms within the smart contract research space, mainly Trail of Bits and Consensus Diligence, who have basically publicly denounced contract upgradability and this proxy pattern because of kind of this immense backwards compatibility risk. And instead of this pattern, they suggest that developers use a strategy of storage migration as preferable to mutation of this like logical implementation. So the problem in the context of Celo and our smart contract developers is asking our users to migrate to a new system is not the same as a Uniswap asking their users to migrate to V2 or a Compound asking their users to migrate. And conducting a storage migration requires that there's some sort of historical storage snapshot captured at some point in time. And when enacting a new contract with this historical snapshot with the new features, there is inherently a downtime between when the snapshot is captured and when the new contract could be activated. Because it's not feasible for a single transaction to read the entire storage state of another contract and use it as its own. So, and especially in the context of our decentralized governance process, where we have actually a bunch of different phases in our timeline for when changes are discussed, to when they're voted upon, to when they're actually executed, this lag time is exaggerated. And we really care about our upgradability process being seamless because it's going to happen on a regular basis as a consequence of our user demographic. We need to kind of adapt to the changing set of users as we grow. And the upgrades should be atomically executable through our decentralized governance process without any sort of downtime or trust in a centralized developer like C Labs to conduct this storage migration safely. We want our stakeholders to be able to, through decentralized governance, assess the safety of a contract upgrade, which becomes difficult to, or approaches impossible with a storage migration. But what we can see both in the kind of Ethereum ecosystem with Compound's governance process, and on the right is actually a Celo proposal, the first contract upgrade we actually performed, is that using the proxy design pattern, upgrade proposals are quite opaque and actually are difficult for the stakeholders to decipher the impact of, because they're essentially required or expected to do pointer arithmetic on addresses. So you can see here, like this Compound proposal looks like it has 4 transactions in it, but it's really difficult to tell like what these memory addresses are doing, and it creates a kind of like information asymmetry between the proposer of a change and the stakeholders who are affected by a change. And this is a big problem. So we felt compelled to design a strategy to attempt to solve this problem and allow our stakeholders to participate in our governance process and our contract upgrades without just trusting the creator of a proposal. So my team, the contracts and primitives team, has been working on this for the past few months, but we've taken great care to adopt a development workflow which acknowledges the risks of using a proxy upgrade pattern with every change that we make to the smart contracts in an attempt to mitigate the disastrous potential of a storage incompatible upgrade, which would break this core functionality of the contracts. And also in an attempt to create an easy to follow audit trail of all of our smart contract changes and upgrades. So each core contract is versioned independently within its bytecode using a semantic versioning scheme that we have come up with to indicate backwards compatibility. So there's actually 4 different units. The least significant unit is or the least 3 significant units should be familiar to anyone familiar with semantic versioning: major, minor, and patch version. Patch is used for backwards compatible bug fixes. The minor version is used for when functionality is added in a backwards compatible way. The major version is used for when functionality is added in a backwards incompatible way, and then to a logical implementation. And then the storage unit or version indicates when there's an incompatible storage layout change, which would require an entirely new proxy and a storage migration, hypothetically. And so our ongoing smart contract development is done on the master branch. Like, we don't want to be working on some special smart contract branch. We want to be able to work on master and integrate with all the other layers of the stack and all their new features to have faster iteration cycles. And we use a custom backwards compatibility continuous integration script that we've come up with to require that the version in each contract's source code reflects the expected diff between or with respect to the latest release version. So you'll see in the upper right here, the master branch is being compared to the latest release, which in this case is our second release tagged with the mainnet environment. And this is how we ensure that at any point in time when we're making changes to the contracts in master, the developer is acknowledging the impact on backwards compatibility. The other component of our development process that is important to the release process is our relationship with OpenZeppelin. So we conduct actually a rolling audit on a regular basis with OpenZeppelin on our smart contracts. So we cut a release candidate branch from our master branch, and we use the CI version check that I mentioned previously to compare to the latest release candidate tip. So this allows us to go back and forth with OpenZeppelin on any issues they identify, while ensuring that master reflects the diff with the most recent planned release candidate. And so once we've gone back and forth and we've made all the fixes to the core contracts that they've identified, we come up with a finalized commit hash that we tag with a release candidate in GitHub. And this tag basically indicates to stakeholders a specific version of the source code where this third-party subject matter expert in OpenZeppelin security team has verified that this specific commit hash or commit tag, git tag is safe according to their analysis. And so what does this mean in the context of our release process? My team has been working on a suite of tools which allows the Celo community to participate in the Celo core contracts being upgraded through decentralized governance, which has the intention of giving the stakeholders increased confidence that all of the changes being made in an upgrade are safe, they're audited, and they're backwards compatible. So they're not going to break the core functionality. And we've done this in such a way that we can even model our team, the C Labs developers, or the contracts and primitives team, as an adversary in this process. So we could assume that we're malicious and the community would still be able to conduct and participate in the upgrade process seamlessly using these tools without trusting us. And these release tools that I'm talking about were actually included in the last round of the OpenZeppelin audit scope, who kind of, as the original architects of this proxy pattern, are a very strong affirmation that these, even these tools themselves are correct and safe, and we as C Labs aren't doing anything malicious. And more detailed information about how to use these tools can be found on our docs. Please check them out after the talk. We definitely want you to participate in this process, but I'm going to be talking about kind of what the tools do under the hood. So the release tooling is intended to be used in 4 phases. There is the verification of the previous release as kind of a sanity check. There is a backwards compatibility check between the current release candidate and the previous release deployed to an environment like mainnet. There is the deployment of the release candidate to the environment. And then there is the verification that this deployed release candidate also is safe. And so using these tools, any community member can build, deploy, and propose for upgrade a release candidate in the source code on a specified environment. So anyone in the community can do this automatically using this tooling, and all of the stakeholders can verify that the release candidate is in fact what is being activated by a governance proposal. So the first step, verification of the previous release, again, is it's just a sanity check that our target environment matches what our git tag specifies. So what we do here is we compile the Git tag that we think is what's deployed. This gives us a set of build artifacts with a specific version in the source code, from the source code. And then we also look up, using the registry, the build artifacts which are actually deployed to an environment. And so this allows us to compare the bytecode and storage, or rather the bytecode and the version, expected version of what's deployed to what we are using in our development workflow. And again, these Git tags are reflective of what's audited. And so once we've done this verification, we can conduct the backwards compatibility check between the current release and this release candidate. So what this step does is it compiles the previous release tag and the candidate release tag, and it compares the smart contracts build artifacts. So we look at a lot of different things here. It's actually quite a complex analysis. And this is what we use in our continuous integration script. But we basically detect if there's any storage, ABI, or bytecode incompatibilities and produce an expected version diff. And then we look at the versions which were acknowledged in the source code and ensure that the actual acknowledged versions reflect what is expected based on the detected compatibility checks. And the output of this step is a detailed version report, which can be reviewed by the deployer of release candidate to make sure, just as another sanity check, that everything looks good. And this report describes kind of these expected and actual version differentials. The third phase of the release process is actually deploying the release candidate. So this, again, compiles the release candidate, and actually using the compatibility report from the previous phase, we deploy the changed contracts to a specified environment. So we use the report to understand which contracts have been changed and which contracts necessitate either a new implementation or an entirely new proxy and implementation pairing if a storage incompatible change was made. And we deploy these contracts automatically, which were compiled from the release candidate tag. And the output of this step is the governance proposal, which represents the core contracts activating this deployment. So the proposal encodes a storage version change as a repointing of a registry address to a newly deployed proxy address. And then if storage compatible changes were made to the contracts, the proposal encodes this by repointing the existing legacy registered proxy to a new implementation, the one that was deployed. And so what we have here is just a JSON of the governance proposal. And at any point, someone can reproduce this governance proposal deterministically and from a release candidate tag. And if they want to, they can propose it in on our governance contract. What's nice about this is that the other stakeholders participating in voting can conduct the same verification steps used by our tooling to fetch this proposal from the governance contract and ensure that the proposal corresponds to an audited and backwards compatible source code version before indicating their support for an upgrade. And to do that, they can verify a release candidate while a proposal is still in kind of the pre-execution or referendum phase of governance. So they can, using the fourth phase of our release process, they can compile the release candidate and using the fetched governance proposal can, using this tool, determine whether this pointer arithmetic happening in the proposal, which is again like quite an opaque and hard to read proposal, they can determine whether this upgrade proposal actually corresponds to the corresponding release candidate version that has been audited and that has been determined backwards compatible by all of our continuous integration tooling. And so this is kind of a what we think is a super novel technique to empowering our stakeholders to participate in the core contract upgrades through decentralized governance without having to trust even C Labs as kind of like the core development team, which I think is pretty cool. So yeah, I would invite you all to definitely check out our docs and try these tools out. We're actually rolling out release 3 right now on our test networks. And so release 3 should be hitting mainnet, a tag that looks something like this, in a few weeks. And I hope that you guys all are excited about participating in this process. And I just wanted to mention really quickly that the Celo improvement proposals don't have to necessarily represent changes to the core contracts. And the other half of my team's work is focused on developing primitives. So we're contracts and primitives, and the primitive side is designing kind of standard specifications for common application use cases, which might involve significant complexity or context around integrating with the core contracts, or kind of require special care to guarantee the same privacy and security invariance that the core contracts maintain. And next week, what you see here is CIP 8. Next week, my colleague Alex Harley will be presenting our work on CIP 8, which is an off-chain storage specification to be used in applications like Valora. I think the first use case is encrypted profile pictures. And so if you're interested in anything I talked about today or hearing more about this primitive, you can join us next week. And if you are really excited about this, we are actually hiring on the contracts and primitives team. So we would love you to kind of take a look at the position and apply if any of what I talked about seems relevant or exciting to you. And with that, I can open it up to questions, but thank you for listening and being part of our community.
No questions so far. Posted it on the Ask a Question tab. Please ask a question if you have one. A very shy set of folks.
I like the polls.
Oh yeah, there's a poll. Those who are still here, could you please take the polls? Your feedback would be awesome.
Could you speak more on the details of CIP8? Thank you, Luke, for the great question. So yeah, I would encourage you to look at kind of the contents of this discussion on the CIP repo, but the main idea is to create a storage standard for network-related transactions or accounts, which don't imply a state bloat on the actual blockchain client. So if we just like stored profile pictures on the blockchain, we would have this like massive storage explosion, which is kind of impacting Ethereum right now. And so our goal with CIP8 is to associate on-chain accounts and transactions with authenticated off-chain storage using a digital signature scheme. And in doing so, like maintaining privacy and security of this storage. But yeah, thanks for the question. Nam asked, what was the hardest thing about establishing the process? That is a great question, Nam. I think you're familiar with a lot of the problems we've run into, but I think figuring out a development workflow which was suitable to creating this trustless contract upgrade was really challenging because there weren't a lot of tools available for this type of verification. So we had to kind of come up with a lot of this ourselves and really pave the way for doing work, and sometimes even had to go back on our development history and decide whether or not something we did was compliant with our new process.
I don't think there's any other questions.
Okay, well, if there's no other questions, definitely come back next week and join us for another discussion from the contracts and primitives team, and feel encouraged to apply to join us if this work seems interesting or exciting to you. But thank you guys so much for joining, and thank you, Judy, for facilitating. Definitely join the Discord. That's a great call out. Participate in our community.
Thank you, everyone. Thank you, York.
Thank you.
Bye.